Hello? First again.
Oh, I'm hungry.
Welcome. Hello? Hi?
Not loading for me.
What's that? Hello, everybody?
Fernanda's coming. Her computer's having trouble booting up.
Okay.
That's what they all say.
I think Maddie said she wasn't going to be here. So we're still missing Emma.
Wait, who are we missing?
Emma. Maddie won't
Okay.
be here. But Emma sometimes has issues with her connection, so. So we'll just start, I guess. All right, we're almost to your long weekend. Just one more class after this. Hopefully you guys are doing all right. Okay. Well, we can start. I'm just going to draw things and try to explain things. Just drawing people. Doodle.
What was that? Whoa, whoa, whoa. Go back.
My people?
Yeah, go back.
I just do like a head, a nose, eyes, ears, hair, and torso. This is like the guy I draw the most.
That's pretty good. I'm not even going to lie.
I don't know how to draw hair though, so all my hair is the same.
It's fine.
But when I kill time, I draw a lot of weird people. Anyway, I could draw you a picture if you wanted.
Can I get the photo? Or can I get the picture?
What's that?
So, can you make me a cool picture or photo or whatever you want to call it?
Yeah, I never have ideas of what subject matter I should draw. Like, I have nothing to draw, so I can't think of anything good.
Draw Will.
Will? I can't draw specific people very well. Like, I can't distinguish their faces. So I can do like a scene or like something, but I can't really do specific people.
Gotcha.
I'm not that good.
Not yet.
Yeah, I'm practicing. I like to do perspective drawings too. That I sort of need a grid for. All right, you guys ready to start? No? Yes? Circle head shake? All right. So we kind of went over last class the big old default hypothesis and the alternative hypothesis is something that we always have. when we're doing what we call hypothesis testing. Maybe better to call it significance testing. Actually, yeah, I'll just do it this way, I guess. All right, so the idea is that there is a true population average, and both hypotheses make a claim about that true mu, the true average. Now, the default, like let's say you want to say that, well, I think your claim is incorrect. So let's say somebody says, I think the average score on some test is we'll say a 65. They say that's the claim. And let's say I don't think it is 65. I want to test to see if it's not 65. So now this is for some big population. So what I would do is I would create a sample of people, not the whole population, and I would find their average. So I would get an X bar for my sample. And if I wasn't already given the standard deviation for the population, I would assume that my standard deviation for the population was pretty much what I have for my sample standard deviation. So if I didn't have the sigma, I would just use my sample standard deviation and pretend like that's my sigma. For now. There are other tests we can perform that are a little different, but this is the basic one. Most of what we're doing all kind of comes down to these basic concepts for the rest of the semester. So I have my X bar from my sample, and I want to be able to say something about mu, the true the average for the whole population, not just my sample. Let's say my average for my sample was 64, not 65. Well, from random chance in the way that I select my sample, it's unlikely. I mean, there's always some error. There's always some ways in which your sample is not totally just like the population at large. But you're hoping that it's representative enough, that it's close enough, that it has the same composition as the population at large. So if I find that my sample has an average of 64, that's not what the claim was. The claim was that it was 65 for the population. But it depends on how big my sample was and what the standard deviation was, which is tells you how spread out the values are. Depending on those numbers, sigma and n, really, and I guess the degree to which I want to be confident. So depending on these things, I may or may not decide that my sample having a 64 instead of 65, I probably am not going to be able to reject the default hypothesis if my number is that close. So just by randomness, I'm not going to be spot on with my sample. So what I need is what we would call statistically significant evidence that that the true average is different than 65. Having a sample average of 64 could very well not be statistically significant. That's not a significant difference. So for all practical purposes, my group and the group that the person is claiming about the population, I can't tell them apart. I can't say that my little group comes from a different population than the one that's being imagined in the claim that was made. So they seem to be the same. So I would probably have to say, not that I go with this, but that I fail to reject H naught. So H naught lives to see another day. The claim survives. I could not show with significant evidence that the average is likely to not be 65. I didn't have strong enough evidence to reject. Does that make sense? Okay, good. Now, if instead of 64, let's say I had my X bar was, I don't know, 60. Well, if I have a large sample size and my standard deviation isn't too high, and I'm not trying to be crazy confident, I'm willing to take a bit of a gamble, a bit of a risk, then that may be strong enough evidence to say that I'm going to reject H naught, that mu is equal to 65. And I'm going to go with, for now, this alternative hypothesis that mu is not 65. So I'm rejecting the default hypothesis based on my evidence. Well, let's say I chose a confidence level of 80%. That means, if, let's say I do this 100 times, well, 80 times out of that 100, I'm going to make the right call to reject. But 20 times out of that 100, I'm going to follow the evidence. I'm going to use the rules of statistics and say, I think I have enough evidence to reject, but I'll be wrong for doing so 20% of the time, just because of due to randomness, just because when I drew my sample, I just happened to get a bunch of people who score really low. I just got lucky in a sense. I got lots of people who score lower and not very many people who score higher in my sample, just by the luck of the draw. And so even though the population average maybe is 65, I may, 20% of the time, I may be led astray by this procedure. But 80% of the time, I'll get it right. I'll make the right call. So that's one thing to keep in mind when you're talking about this confidence level. You can be confident you will get it wrong a percentage of the time following these methods. You can be very confident that you'll be wrong plenty. But it's not really about getting it right every time. It's about making a better guess, making a better gamble, making a better decision, making a more informed decision, and having the odds in your favor that you're going to be making a good decision, but never being guaranteed of that. So that's an important thing to keep in mind. Does that make sense to you? No, Emma? So that's statistics. Like there's a procedure. It's not really math. It's more of a science. It's a quantitative science. Its results are not certain because they're about the world, and you can never really be certain about the world. You can't have pure certainty. In math, where you're just talking about abstract things that are so defined, you can have certainty. But as long as it's about the real world, certainty isn't perfect. So you have a level of confidence, and that's really the best you can do. Okay, so how does the significant test work? Well, there's really three ways in which the tests are performed. There's three different ways you can do it. They're all basically equivalent. So the idea is that, okay, here's some number line. And let's say somebody claims that the true population mean is 65. And we know something about the standard deviation. I don't know. Let's say it's, I don't know, 5. Yeah, I guess so. We'll go with 5. I'll go with 7, just to make it a little wider. All right, so what we're going to get is what we're going to do in order to test this is, well, there's a couple of ways that we can do it. What they all basically boil down to is we don't know what the true population distribution is. There's no way to know that unless you do like a complete census and you measure everybody, which is usually too much work, too expensive in terms of time and resources. It's not really feasible to get everybody. But you can create a sample, and if it's big enough and the data is not too problematic, that could be all you need to be able to make a better guess. So how do you test a claim when you don't know the thing that the claim is about? We don't know the distribution. So how do I know where it's centered? How could I know where it's centered? Well, so before I go into that, if we go back a little bit towards the beginning, and I tried to explain kind of like the roadmap of what was all involved in statistics and the different parts of it. Remember we had descriptive statistics. That was one thing. That was how we summarize lists of data, and we come up with things like this is the average, this is the mean, this is the mode, this is the median, this is the range, this is the standard deviation, this is, whatever. This is the proportion. These are ways of coming up with numbers that summarize the lists in various ways, summarize the list of data. So descriptive statistics is just how do you come up with a stat, how do you come up with a parameter, how do you summarize a list. It doesn't really help you know things about stuff that you don't know. And then there was probability theory, which was the idea that if you know everything that's inside of a bag, so I know that there's so many clear marbles, but there are so many solid colored marbles and so many striped marbles. If you know what's in the bag, if you already know the composition of everything that's in the bag, the whole population, I can tell you what is the probability of reaching into the bag. I'll try to do a hand for you guys. That's like the hardest thing for me to draw. There's fingers. There, that's a hand, I guess. Oh, I messed up my thumb. Anyway, I tried. So I reach into the bag and I get so many solid marbles, maybe a striped and a clear. So with probability, if I know what's in the bag, I can tell you the probability of drawing out a given hand. So this hand could be, 10% chance that I would get this hand or this draw, or there's a 3% chance I would get this draw. There's a 0%, like 0.01% chance I get this draw, all stripes, or there's a 30% chance I would get all solids, If I know what's in the bag, probability allows me to calculate the chance of me drawing out some particular subset. It's inferential statistics, what we're talking about now. not descriptive. It's inferential statistics that allows us, without knowing what's in the bag, to take out a drawing, like a sample, and try to say with some confidence, what is the composition of the bag? So without peeking, without knowing what's in the bag, can we draw out a sample, look only at the sample, and then know something about the population? Well, we can't with perfect certainty. We can't know it 100%. But we can find the proportion of solid marbles within some range. We can create a confidence interval. Or I can test your claim about what's in the bag and have 80, 90, 95% confidence in rejecting your claim or in not rejecting your claim. I can't know with certainty, but I can make a decent bet if I get to see a representative sample from the bag. Even without looking at the bag, this is the best I can do at trying to predict what is actually in the bag, or at least coming up with a range of ideas of what's in the bag, what's likely to be in the bag, and what's unlikely to be in the bag. Are you guys following that? Okay, so as a science, like the default position that you assume is that, everything can be explained and that you don't witness any miracles, that there's nothing miraculous going on. A miracle basically is an event without an explanation. And you never go with that, you never assume that. So what you do is you make a guess about what's in the bag. You don't know what's in the bag, but you come up with some claim or you come up with some guess of what's in the bag. And from that, you build a model. It's a theoretical model. It's not true, but you make a guess at what's in the bag. You model what's in the bag, which may or may not be accurate. And then you pull out your sample and you calculate the probability. If you know what's in the bag, you can calculate the probability of any draw. Well, you don't know what's in the bag, but pretend you do. Make something up. Come up with a model of what's in the bag. Make the numbers up. And then draw out your draw. Look at your hand. Look at the sample. And based off of your model of what's in the bag, based off of your guess, look at the probability of getting that draw if the model is accurate, if the model is true. How likely would it be for me to see what I'm seeing right now? If the hand I drew would be completely improbable, it would be so unlikely for me to get this draw from the bag if my model were true. This would be a miracle. Well, you don't assume that it is a miracle. You assume that it's average, it's normal, that your hand represents what's in the bag better than your guess does. And that's when you reject the guess. You reject the model. You assume that you haven't seen this super unlikely event. You assume that your model was wrong to begin with. That's how you're able to reject the claim. It may not be perfectly right. You may not get it right every time, but 9 times out of 10, you're going to win the bet. You're likely to be right. Improbable things really do happen, though. Merely miraculous events almost never occur, but they occur all the time, every day, everywhere, because so much is going on that crazy things do happen. Even life itself. It may be a completely improbable thing for life to arise, but it's done it. And once it's done it, it keeps going. So it is possible for crazy things to happen, but you're just not going to bet on it every time you play. Every time you spin the wheel, you're not going to bet on the most crazy thing to ever happen. It's going to happen again when I spin the wheel yet again. So you build a model, you make a guess at what's in the bag. You look at your drawing, your sample, And if your sample is freakishly unlikely, you just assume that your guess was wrong. But if this was a somewhat likely thing, like if your model is true, then I would have like a 50% chance of drawing something like what I see. Then I can't reject it. Then the models could very well be true. Like, I had a 50-50 chance of seeing something just like what I'm seeing. So the model cannot be rejected. I don't have the evidence to reject it. Does any of that make any sense? Okay, good. So that's what we do. We guess. That's all science. You guess, you test it out, and were the results different than what you calculated, like super different, then you guessed wrong. But if they're really close, then that guess has survived for one test, and maybe you'll test again. All right, I'm going to undo this and do that line again. Okay. So I've got this number line, and somebody tells me, oh, I think, oh yeah, and sigma was 7. So the spread of the data in the population, we know that they're kind of spread out in a way that the standard deviation, the average spread is 7 units or points or whatever. And someone tells me, well, the middle, so I mean, with sigma, we know the shape of the distribution. But the question is, it's like pinning the tail on the donkey. Where is it centered? Where do I place this distribution? Where ought it go on the line? Someone says, I think it's at 65. I think that's where the symmetry point is. I think that's where the true average is. Well, we don't know. So what are we going to do? Pretend it's true. We're going to make a model around the claimed mu naught, the claimed, the guess. We're going to build the model as though the guess were true. And then I'm going to take my sample. I'm going to take their average, x bar, and I'm going to put it on the line. So here's x bar. All right. So x bar is not exactly where mu is. Maybe x bar was 60. I don't know. But I have the shape of the curve. And I know from the shape of the curve that if I go 7 units this way, my curve isn't drawn very well, and 7 units this way, then I should have about 70% of all values in this range. Within 2 standard deviations on each side, I would have 95% of all values. And within 3, I'd have 99.7. But I'm not even one. Okay. I'm not even 1 standard deviation away from the middle in this case. So my curve should actually probably look more like, I don't know. It should be wider than I've drawn it. But just accept that my model isn't as wide as it should be. Or I should put 60 closer. Maybe that's what I should do. So if my x bar is 60, it's probably closer to here. All right, so what I do is I say, okay, if here's x bar and I'm 5 units away from the claimed mu naught, and then I go 5 units on the other side. So these values in that range, in this range, are closer to the average than what I got, than what I drew. So anything closer is stronger evidence that the model's good. anything as far away from the middle as I am, or even further, would be evidence that that the model's not that I got something that would be very unlikely if the model were true. So this region out here, I don't know what I'll use, all the way, and this over here, these represent the values that are further from the middle than what I have, that are even less likely according to the model. So the idea is that if you take the things that are further, that are less likely than what I got on this model, that's what we call the p-value, lowercase p. So when you like when you do the normal CDF, you get a p-value. Here, this is called a two-tailed test because I'm checking to see if mu is not equal to 65. So I don't care if it's less than or greater than. If it's just further away than some amount, I'm going to reject the guess. So what I do is I take my p-value, and we can go ahead and do this. I'll do a test run of it in just a second. I guess I'll do that right now. So let me pull up my little normal distribution thing. Okay, I said that the guess where the middle was 65, the standard deviation was 7, and I'm at 60. So I typed 30, okay, and I'm at 60. So on one side, to the left, I have, just almost 24%. Which means if I take a point just as far on the other side, like right here, and cut off that wing, then all the points that are further away from the middle than I am would be double this if I included the second wing. So instead of 24, that's 48%. So if the model were true, there would be a 48% chance, that's almost a 50-50 chance, that I would get something as unlike the model as I got, or even further from it. So that's not that hard to do. I had a 50-50 chance of getting what I got if the model were true. So I'm not able to reject because that's too high of a likelihood based on the model for my draw. But let's say my draw was something like, we'll say 50. Let's say I got an average of 50. Well, now there's a 2% chance on this wing. And if I include the other wing, that means there's about a 4% chance, not even, of getting what I saw. So if the model is true, then I've just witnessed something really hard to do. There was only a 4% chance that I would get something this far off from the model if the model were true. So that means I'm likely going to reject the model. If I have that low of a chance of seeing what I just saw, provided the model's true, then I'm guessing I didn't just see some freak of nature accident. I'm guessing the model is wrong because the probability of what I saw with my own eyes was so low, according to the model, that the model's got to be wrong. Like, I didn't just draw 4 aces, like after a clean shuffle. Like, that's unlikely. Either it wasn't a clean shuffle. I mean, that's what you would assume. If you drew 4 aces right off the top, and someone's like, I shuffled that well, you'd be like, I don't think you did, because you would throw out the model, because what you saw was too unbelievable according to the model. Um, so that's kind of how this works. You have a p-value, and let's say my p-value was 4%. That's what I calculated the likelihood of my draw to be, my sample. Well, what confidence level do you want? What confidence level do you think we should use for this test? Any guess is fine. Or any choice.
Do 95.
95? Sounds good. So if I have a 95% confidence level in the calculator, I would enter that as 0.95. That's my C level. So what is my significance? That's given by the symbol alpha. It looks like a little fish. It's Greek letter, first letter of the alphabet, lowercase. Alpha is my significance. And so alpha is going to be 1 minus my confidence level. So that means my significance is at a 0.05 level, 5%. It's the complement of the confidence level. So how do I perform my test? I basically compare my p-value to my alpha. And if p is less than alpha, my significance level, then I will reject the default guess. But if my p level is greater than or equal to alpha, I'm going to fail to reject the guess. What am I doing? That's how you perform the test. That's one of the ways. You calculate the p-value, you take your confidence level, and the opposite of that is your significance. And if you got something more rare than your significance level, then you have reason to reject the claim. So my 4% is smaller than the significance level of 5%. So that means I am going to reject the guess. I do not believe that the middle was at 65 because what I saw was so different and was so unlikely, assuming that was true, that gives me reason to not believe it. Is that okay? Awesome. That is one way to do this test. So, yeah. And that's using the p-value. I'll just briefly describe the other ways. We won't go into them until we meet again next week in person. But the other ways, so one you can put the one way was the p-value. You put the thing on the guess, and then you compare where your X bar was, and you check to see, is your significance, is the p-value, is it less than your significance level, which is based on your confidence level. That's one way, p-value. The other way you could do it, which is equivalent, is you could say, just like how we did the confidence interval, with the confidence interval, we said that, okay, take your sample average plus or minus your margin of error, which is based on your confidence level. And that gives you the range of, that you'd be at X bar minus E and X bar plus E. That'd give you an interval. Does that ring a bell? So this other way of testing a hypothesis is building a confidence interval, but putting the middle as the guess. So you're going to build the model, put it where they claim it is, and add or subtract your margin of error. And then check to see if on your interval, so here's the guess, here's the guess plus E, and here's the guess minus E. If X bar is in the interval, you can't reject the claim. Okay. But if X bar is outside of your interval, then you can reject the claim. Okay? And we'll go over how to do that in the coming weeks. The third way is with a test statistic. And that's pretty much calculate the z-score given your value. So the z-score for my value is going to be my X bar minus the guess. So pretend like the guess is correct. And then divide that by your standard error. Okay. And then compare that to the critical z-score. If you're further out away from the middle than this critical z-score, so like if I look at my thing again, so here's my z-scores up top. A critical z-score for 95%, I believe, was 1.96, almost 2. So that's for 95%. 99% was like 2 point something. Pretty much once you get past 1.5, things are becoming unlikely in either direction. So if you have a z-score that's beyond 1.6 or 1.8 or 1.9, you're probably going to reject the guess because your critical z-scores are around there, 1.645, 1.96, and beyond. So if you have a z-score that's bigger than 2, you're rejecting pretty much. Even if it's bigger than 1.5, you're getting very close to rejecting. But that's the 3 ways. You can go by your test statistic, your z-scores, and compare it to the critical z-score, which is based on your confidence. You can compare where your X bar is against the confidence interval, which is wide based on your confidence level. Or you can create a model of your distribution, figure out the probability of being further away than what you got, and compare that to your significance level alpha, which is based on your confidence level. So all 3, I'll do a different color, by being connected to alpha or being connected to the margin of error or being connected to your critical score, they're all related to your confidence level. And they're all ways of deciding whether or not you will reject the guess or not. Does this make sense? Any questions? All right. Well, those are 3 ways to test a claim. I don't have an assignment for you, so you guys get to enjoy your long weekend. And that's pretty much it. So try to remember what we just went over. Try not to forget it over all those days. I will see you when? Wednesday?
Wednesday.
Hump day, okay.
Well, we love hump day.
All right. You guys have a great weekend.
Yep.
Bye.
See ya.